Okay, today we're going to look at some applications of exponential growth and exponential decay. Some of them you may have seen before. We're just going to kind of work through them. And different people will set these up differently and use different formulas. I generally just stick with one formula to make everything nice and straightforward and simple. So that's what I'm going to use. But be aware, some books, and if you look at other videos online, they might use different equations. They're basically the same, but they look slightly different. And essentially, the equation we want for exponential growth and decay is just going to be A equals A initial e to the kt. By now, we're used to this A sub 0 thing. That just means your initial value. K is your growth constant. It's a constant, just like when we solved variation problems before. For most problems, we'll have to find a way to solve for it by plugging in some values. The same as when we did variation problems earlier in the semester. So for the sake of argument, suppose the population of Nashua, New Hampshire, my hometown, is 500. That's not true, but we use it for this problem. In 3 years, there are 900 people. How many people will there be in 20 years? Okay, the population of Nashua, New Hampshire is 500. In 3 years, there are 900 people. How many people will there be in 20 years? So population growth is exponential, so we're going to use our exponential equation right here. And all we do is A equals A initial e to the kt. That's my initial value. For this one, I'm told the population is 500. So I'm going to let A initial be 500. Now, I just need to solve for k, my constant. We said before with our variation problems, the way to do that is to find an a and a t that are related. And in this case, in 3 years, there are 900 people. So when time is 3, a is 900. So we can plug that in. 900 equals 500 e to the 3k. Now just solve for that. And there is an algebraic trick for this. We used it when we solved regular exponential and logarithmic problems. And we use it a lot with applications. We want to solve for the k, which is the power of the exponential, so we have to isolate it. So get rid of the 500, divide it on both sides. We get 900 over 500 equals e to the 3k, which we can just reduce to 9 over 5 equals e to the 3k. Now, we need to somehow bring the k down. We know from our properties of logs that if you have the log of something raised to a power, the power comes down in front as a constant. So use that. Take the log of both sides. Or, since this is e, use ln, the natural log of both sides, because then ln and e cancel each other out. They're inverses. So, we get ln of 9 over 5 equals ln of e to the 3k. ln of e, they're inverses that cancels. So I'm left with ln of 9/5 equals 3k. And then just divide by 3 on both sides. And that will be my k. And now I have my calculator here so we can kind of work all this out. So let's see. That's ln 9 divided by 5 divided by 3. And we get 0.1959. One thing I would stress, don't just use 1 or 2 decimal places. You'll end up with a lot of error when solving these. So we're going to use like 6 of them just to try to curtail the error. So 0.195929. And there's my k. So going back over here to my original equation, I can rewrite it, and I get A equals 500 e to the 0.195929 t. Now I have an equation. Now I can actually solve the problem I'm asked, which is how many people will there be in 20 years? That's what is A when I know time is 20. Plug it in and solve. So we get A equals 500 times e to the 0.195929 times 20. And then just throw it into your calculator and get an answer. And again, for the purposes of this, we'll get 25,164. There we go. And that's logical. It makes sense. The population is growing from 500 to 900 in a couple of years. And then like almost 15, 18 years later, it's up to 25,000. So that works. As far as it goes, that's pretty much all we need for exponential growth. We just need to know the formula. A equals A initial e to the kt. But to do one more example, instead of using exponential growth, we're going to use exponential decay, which just means something is going down, decaying, getting smaller. So we'll say this. My car is worth $20,000. In 2 years, it is worth $16,000. When will it be worth $10,000? We'll assume that the decay rate of my car, the decay rate of its value, is exponential, which means I can use the exponential equation right there. And we set it up the same. A equals A initial e to the kt. A initial is my initial value, which is 20,000. So A equals 20,000 e to the kt. Just like before, nothing changes. I need to find k, so I need an A and a t that are related. In this case, when time is 2, it's worth 16,000. So 16,000 equals 20,000 e to the 2k. And now do all the exact same algebra to solve for k. Divide by 20,000 on both sides. 16,000 divided by 20,000 is 4/5, which is 0.8. So 0.8 equals e to the 2k. Now, how do we bring down the power? Take the natural log of both sides. ln of 0.8 equals 2k. Divide the 2. And you get k equals ln of 0.8 over 2. Which again, really quickly, negative 0.111572. Carry it, like I said, to about 6 decimal places just to avoid error. And one thing I'll point out, here my k is negative. That's what tells you it's a decay model. Our previous k was positive, it was a growth model. If k is negative, it's a decay model. Some books, and if you watch other videos, they might actually have this equation for growth, and then for decay, they'll say A equals A initial e to the negative kt. You can do it that way if you want. It doesn't really matter. I prefer to just use one formula. Let the problem itself dictate what k is. Here k is negative. It's a decay model, which is what I want. So that's a good thing. But now, rewrite my equation. So I get A equals A initial, which for us was 20,000, times e to the negative 0.111572 t. And now answer the question you're asked. When will it be worth 10,000? Here, I'm looking for time given an amount, so plug in the amount. 10,000 equals 20,000 e to the negative 0.111572t. Now do all the exact same algebra we did here. Divide the 20,000 over. 10,000 divided by 20,000 is 1/2. So 0.5 equals e to the negative 0.111572t. How do I bring down the power? Natural log of both sides. So I get ln of 0.5 equals negative 0.111572t. And now divide by negative 0.111572. And that's my t. So we get $6.2 years. And there we go, nice and straightforward and direct. As far as these go, we're going to look at a few more examples, different types of examples that can pop up in the next video I do with this. But essentially, you need that equation right there. Plug in the information you know, whether it's the initial value, whether you're given a point, somehow find k. Once you have k, put it back in the equation, and then maybe solve something else. And the algebra is always the same. The biggest trick is right here, when you take the natural log of both sides to bring the power down. We use that over and over and over and over again. Like I said, this is a couple of examples. I'm going to stop this video now because it's rather long. And I'll do another one with a couple more examples of exponential growth and decay.